So here it is. So hello to everyone. I'm Matej Polzelnik. I am the developer. Just a second. I'm a developer at CozyLab, and today I will gonna be introducing you to the basics of accelerator control systems. First of all, who are we to talk about control systems? So basically, in 2001, CozyLab was founded. Basically, after a group of students developed a control system for a German accelerator Anka, and from then on, yeah, we grew to the 10 locations worldwide, and we have more than 200 people employed, more than 20 PhDs in the STEM fields. So, yeah, this is our footprint in the control systems all over the world. So, yeah, we've been involved in quite a lot of projects, and yeah, our areas of expertise are actually particle accelerators, but yeah, we shifted to the other quite hard stuff and technologies. So one of them is fusion reactors. We are working on the ITER project, radio telescopes in ALMA, and also in space, and some industrial project as well. So what are our main strong points? So because we offer services and products which require expert knowledge. And why is this needed? Yeah, because you need, for the particle accelerator, you need state-of-the-art hardware and software. And we can integrate them to these mankind most complex machines. And yeah, we also offer turnkey control systems adapted for each accelerator. And yeah, we also offer integration of subsystems. And why this is important, it will be apparent in next slides. So first of all, let's go into a brief overview how our particles are accelerated. So as you know, in electromagnetic field, it turns out that the particles they get accelerated. So the component for that actually accelerates the particles is the electrical component, and it's the easiest way to accelerate the particles is with oscillating radio frequency, so sine wave actually. And for example, for electron gets accelerated in this part of the oscillation or sine wave, and on this part they are basically decelerated. And also, yeah, for in some kinds of accelerator, you also need to basically you need to steer the particles, and yeah, the particles are steered using the magnetic component of the electromagnetic field. So let's check some of the accelerator types that the control system. So first of all, let's talk about synchrotron. Okay, if we check the synchrotron, yeah, here is a source. It goes to boost rings that basically lifts up the energy of the particle, and then which are basically smaller accelerators. And then after all these boosts, it goes to the main ring. For example, this is Large Hadron Collider. And the good things about synchrotrons is that basically they need only one radio frequency cavity. Radio frequency cavity is a device that actually accelerates the particles. And yeah, but all over the ring, we need to ensure that the particles are circulating. And we can achieve this with bending and focusing magnets. And yeah, here in the picture is depiction of a simple depiction of Large Hadron Collider, and the Large Hadron Collider can achieve the energy to the 6.5 tera electron volts. Okay, the next ones are Linux. So these are straight accelerators. Basically, they accelerate the particles in line. And here, basically, we need a lot of cavities and not that much of magnets. So basically, all these are cavities, and you need to ensure that when, in this case, if the source is a proton, you need to accelerate to have a negative electromagnetic field here, so that the proton get accelerated, and you have to synchronize all the cavities, so that that when the particles passes the cavity, that the electromagnetic field is negative. And yeah, here you need just you don't need so much magnets. You just have to fix some of the positioning, but in actuality, you need a lot of cavities, and these cavities needs to be superconductive. And for example, in synchrotrons, yeah, the bending and focusing magnets need to be superconductive, and I will talk a bit about this a bit later. And the last one is cyclotron. Cyclotron basically is an accelerator that have two big electromagnets on each side, and you have the particle source in the middle, and when you shoot the particle in the particles starts to bend in this pipe and are accelerated through these cavities. And okay, that's a really simplified version of it. So okay, let's check and what does these elements look like. Okay, ion source. For example, here is the ion source for hydrogen. Here is the hydrogen tank, and then you put the hydrogen into this chamber where here is an electromagnetic field that separates the electrons, and only protons, only hydrogen proton stays, and then you extract them and put them to the accelerator. And you put them into the pipe, into the beam pipe, and in the beam pipe you need a vacuum. Of course, if there is any, you need to ensure that there is no particles actually in these pipes, so that the proton has basically a free way through the line. And yeah, this is done with the vacuum, and there is a lot of vacuum pumps in accelerators to ensure that the pipe is clean as it should be. And then magnets. Magnets are essential for steering and focusing of particle beams. And for example, in synchrotron, yeah, the steering is essential, and it has to be performed in very synchronized, very synchronized. No, because yeah, the particles are constantly circulating into the ring, and you need in synchrotron there are high energies, and you need really strong magnets that are usually superconductive, so that they are able to provide this high magnetic field that is bending them. And for this, dipoles are used. Dipoles are basically two magnets that is just they are forcing the magnetic field in this direction, downside direction, then and the particle is steered. Also, you need quadrupoles. Quadrupoles are basically magnetic lenses. So if the beam gets a little bit uneven, you can focus them with these quadrupoles. And yeah, usually when the particles transfer or pass through this pipe, and in the quadrupole, they got focused into just one direction, and that's why you need you need quadrupoles in pairs. So, and the second one has to be 90 degrees rotated, so that they can that you focus that in both ways. Okay. And to power these magnets, you need power converters. Basically, these are machines that or devices that deliver power to the magnets. And in one case that I had experience in, the power converter's output was 3.3 kiloamperes, for example. So you see, you need a huge amount of power to power the magnets. Okay, so the next stuff is RF cavity. Yeah, this is the main component basically of all accelerators. Yeah, it's the RF cavities are, yeah, they have particular shape just and you insert inside the radio frequency wave, and if you put the correct radio frequency wave, basically it starts to oscillating in between these yeah, in this shape. So the biggest RF electromagnetic field is here, and it got so it accelerates the particles. And yeah, you need to be very careful how to and precise how to control these RF cavities and how to feed them. So you feed them with klystrons. Klystrons are basically electromagnetic field amplifiers with which you basically then feed the RF cavity. Klystrons are also powered with modulators, which provide power to klystrons. And then you have low level of radio frequency. Basically, that is a regulation of EM field cavities. And here is a diagram how this regulation, how this closed loop is performed. Okay, and I was talking about superconductivity a bit before, and why do you need superconductivity? In case of synchrotrons, I already said that to achieve such high power, so the magnets can bend the particles, you need superconductive magnets, and this is achieved in basically close for some materials close to 0 kelvins. So that's why you need to have a cooling system, and cooling system, yeah, basically it's a huge refrigerator for helium, and this basically you get and then yeah, with helium you can cool down the magnets in case of synchrotrons, but in case of Linux you have to cool down the RF cavities because in case of Linux you need RF cavities to have to be superconductive, because you need a big electromagnetic gradient to accelerate the particles. So yeah, basically, when you refrigerate the helium, it becomes liquid, and then you it encapsulates the RF cavities, for example. Yeah, it makes them superconductive. So yeah, there are a lot of cryo modules, for example, in Linux, and these also have to be really precise. And yeah, the next is, of course, diagnostics. If you don't know where the beam is, you don't know how to steer or focus them. So that's why we have beam position monitors, and actually, yeah, this was presented just before me. So I will just go quickly through this. And now we came to the interesting part. So the timing is and synchronization are the biggest parts of control system for accelerators. And why you need this? Because of course, yeah, the processes in the accelerators are so fast that you have to manage them in some ways. Basically, if there are two ways to synchronize the accelerator devices, and one is RF reference, and RF reference is basically input to LRRF, which is ensuring femtosecond phase stability of EM fields in cavities. And then all the devices take from this stable reference, and to which they regular their output. And the other type of the timing and synchronization system is event timing system, which is basically a precise synchronization of devices with hardware triggers. And you can have a picosecond synchronization or nanosecond synchronization for heavy particles. And yeah, here is a big challenge in timing system. Basically, these are distributed systems across the accelerator, and you have issues with cable length delay, and you have to compensate for it. And yeah, there are basically two really important solutions. One is Micro Research Finland, which are basic flow is depicted here, and White Rabbit timing system, which is depicted here, and this was basically developed by CERN. And we have also some homebrew timing system. And yeah, event timing system is basically like like playing a piano. Basically, you need to put out the commands very fast in extreme and accurate sessions. Okay, some other devices that are really efficient for, that are very important to the accelerators and the control systems is machine protection system. Basically, this system protects the device. So yeah, typically required, for example, to get a picture, the typical required response is times is couple of microseconds. And because machine protection system is placed all over the, for example, synchrotron, we are talking about distributed system again. And you have the cable length that is also challenging this machine protection. So, for example, one cable delay is around 5 microseconds, and you have just a couple of microseconds to respond to prevent the damage to the machine. And how to mitigate this this issue is basically with topology of the control system and the network. And then you also have personnel safety system, so the system that preserves injury or death in the personnel. And there are also other experimental stations, and all these that I was talking about needs to be somehow managed by a control system. Yeah, our main focus is to provide control systems, and we have hardware and software-based systems that are conceptually separated into several tiers. So, okay, the bottom tier basically directly connects to the actual devices, and that we mentioned in previous slides, so magnets, vacuums, LRF, and it access to them, this lower tier access to them on physical level, and on this lower level they do some local control, and also, which is even more important, they expose the signal to the network, and from there, for example, you see here the timing system. So the higher tier can also put out some commands to the lower tier and to synchronize everything, that it works in a synchronized and orchestrated way. Also in the higher tiers there are databases, basically where you store the configuration of devices of different types of accelerator cycles. So basically for every accelerator cycle you need a new configuration on each device that performs the correct tasks. For example, in bending magnets, you need a stronger magnetic field to bend the particles that are faster than the previous cycle. And then, of course, in this middle tier is also MPS, machine protection system. So they basically and the basically MPS network. So so that you have a good overview where the problem can arise, and so that the system can prevent to the further damage. Also, we need archiving, of course. Basically, if you're doing some experiments, it's good to have a certain data, and of course logging. So if when you are developing and building up and integrating the system, you need some kind of logging to check what went wrong or went right, or so on. And then also there is a presentation level. Presentation level is basically for the they are the UIs for the operators and technicians, and for overall visualization. And it's essential to have a common framework, so the devices behave in a consistent way with each other. Yeah, and there are big issues if you have some devices that they don't really understand each other. And also you need to have a good understanding of physics, so that you know how one device interacts with other and so on. And what does it take to build a control system? Yeah, first of all, this is only 10% of the entire project. Control system accelerators are huge and complicated, and there is other really important stuff, and basically teams that work on cooling, vacuum, power, radio frequency, and so on. And yeah, but control system is just one part of the entire project, but it's a essential and needed part. Basically, you need a technological and scientific knowledge, because if you don't really understand how other devices interact with each other, and if you don't know physics behind some of the, for example, the diagnostics tool, basically it's hard to implement a good control system. Also, that is essential is that you have good project management. Why is that? Yeah, well, you have a lot of teams that are working on one accelerator, and you need to coordinate between them. So, for example, there are a team that is working on power and power delivery to the magnets and all the other devices, and basically you need to have a coordination how to perform different tasks. And yeah, I was talking about before about how these processes are very fast, and that you need also very fast and controlled design of a control system. Because yeah, as I was talking, there are just slow response times, and if you don't have a good design and architecture, yeah, can also everything goes sideways. And also you have hundreds of devices, and they all needed to be controlled and monitored. And yeah, there is also the synchronization part of this. And in the end, you need experience. When I first came to the Cozy Lab, I thought, yeah, it's easy. You have devices, you connect them, and you have some control behind them. But it turns out that's just not the case, because you have so much incompatible devices and interactions that you need to be really careful which devices to choose. And yeah, we are here and we gathered a lot of knowledge about this, and so that's why we offer services and products which require expert knowledge. We learn how to develop state-of-the-art hardware and software, and we know how to integrate this software and hardware into these mankind's most complex machines. And yeah, we have a knowledge of integration of subsystems and equipment and everything. So let me just talk about two of our contributions. Basically, Medostron. This is the facility in Austria that is designed to be one of the most advanced centers for ion beam therapy and research in Europe. And Cozy Lab, as a partner, has contributed substantially to the development and integration of accelerator control systems, and also safety systems and medical front end that deals with patient irradiation. And this machine, this is a cyclotron. Right now, they have treatment with carbon ions. And the last and the most recent one that I am also working on is light system by Adam. Basically, it's a LINAC for image-guided hadron therapy. So yeah, this is another attempt, a bit different attempt with for proton therapy with LINAC that I don't think was developed yet. And yeah, the benefits of this system is that it will reduce the cost of building a proton system. And yeah, that's it. Thank you.
Okay, thank you so much, Matej, for your very interesting presentation on these control systems. We'll take a few moments for questions.
Okay, could you please describe control in some simple words? Yeah. Okay. Yeah, it's a bit hard to describe it in simple words because there is so much. But for example, let's say that you're building a house and basically you choose everything that needs to be put together, but you basically need to know how to put it together. So you need someone to tell you, yeah, this, for example, the floor heating needs to be put in this way, and that's also the job of the control system. Basically, it tells every device when to do some stuff. For example, when magnets need to bend and at which power they need to, how much power needs to be delivered to this magnet so that they can bend in the right direction.
If I may intervene, control systems are normally part of core subjects in electrical engineering, even in mechanical engineering nowadays. So I would recommend those of you who are not privy of control and systems to possibly follow courses on that, and maybe pick up a book or two, and incidentally, even in professional organizations, there are a number of journals where control systems are treated as a specific field and area of specialization. So we can proceed with the next question. Thank you, Marius.
Can we use the superconducting magnetic field in LINAC for more efficiency? Basically, you don't need it because in LINAC, the particles are going in the straight line. You just need some smaller corrections and that's it. And for that, you don't need a superconducting magnets. What actually are quadrupoles? Okay, yeah, quadrupoles are basically magnets that are that have basically four. Basically, they have four. For example, dipole is. Yeah, it's hard without a picture, but basically quadrupoles generates four magnetic fields, actually, and two magnetic fields. So in the, for example, let's say up-down direction and the left-right direction, and basically you just a second. No, basically they are and so they focus this with the magnetic field that is basically in a kind of this shape. basically then you focus a bunch that is elliptical. They basically focus it to the more circular pattern and basically put them together. What does RFK mean? I'm not, can you please elaborate? I'm not sure. Oh, was this on LRRF slide? RFQ, okay.
RFQ, I think.
RFQ is, so RFQ are basically radio frequency quadrupoles. So this is basically the same as quadrupoles, yes. Piano is a very good example, but you need the feedback and feed forward as well. Yeah, of course, but yeah, it's just a simplified version. How to present something, you know. Is there any false event that you have to fully shut down the accelerator machine? Actually, false event, yeah, it could happen, and that's why you have conditioning of the and commissioning of the accelerator. First, when you are building the accelerator, you have to check all the components, and then you have some test runs, and you check what can go wrong, and then you can implement this into your control system. Also, I remember there was one big event that you have to fully shut down the accelerator, and that was actually in LHC on a Large Hadron Collider. And yeah, in this event, I think one of the monitors, I think it was beam loss monitor, didn't detect correctly the loss of protons, and basically the protons damaged the walls of the accelerator, and then it had to be shut down for a year, I think a year or something like that. Can you explain a little about accelerator control architectures like LSA, for example? Well,
Matej, your camera has moved upwards.
Oh, sorry. Okay. Basically, we would need a lot of time to go into accelerator architecture, because basically for each of the accelerator you need a different architecture, because most of the time when you're developing an accelerator, or yeah, most times you develop accelerator on the thing that you want to produce. For example, if you want to produce a certain proton that will shoot into the person and irradiate tumor, basically you had to develop accelerator and also the architecture according to this accelerator. So basically all the architecture vary in some cases. So that's why it's also that hard to develop good and efficient control systems. Yeah, here in CodeLab we had a lot of trial and errors. I mean, basically you have to learn and you have to develop and you have to adapt. And I think this adaptation is the basic sustenance of the team that is developing a control system. Do you have some kind of monitoring system running at your control system? EA, Nagios. If yes, which parameters are monitored? I don't really know what is Nagios. but yeah, usually we have a kind of a monitoring system that is basically we mostly use WinCC or Epix. I'm working with WinCC, so that's why I work. And basically, the WinCC gets for example, gets the devices parameters from another in-house developed system that basically bunches all the devices together and then exposes the parameter and all the devices to the monitoring system. So, for example, when I was talking about power converters, basically you have to show all the parameters for example, for power converter that is delivering power to the magnets or any other. Or then you have, for example, I was just working on a device called sliding shorts, and these sliding shorts is basically a stepper motor, and you can, in the monitoring software, you can control this encoder to be really precise and to basically control and fine tune the device that will be working on the accelerator some time back. Okay, next one. For medical systems, patient safety will be the focus. Does that change the way you approach the design of the control system? And do you have examples of specific safety control system found in medical applications? Yeah, of course. And when we are talking about medical systems, then of course you have to oblige the medical standards, and basically that around these medical standards you also have to develop the control systems. And yeah, of course, yeah, this is totally a different case than in just a scientific version. And yeah, we actually are another group in the company is also working on this, and yeah.
Okay, Matej, thank you so much for the questions that you have answered and for a very interesting talk. We will now stop for a short break. We are quite late, but that's also because we've had many questions and we chose instead to answer those questions. So we will now break off for 10 minutes and we will be back at 11:20. Thank you.
Yeah, thanks for inviting us, and we are happy to be here.
Our pleasure.
And
thank you.
Have a nice day, of course, and a good coffee break.
See you. Bye. Okay, see you all at 11:20. Thank you.